two things. The very first thing, you have got this question also in your digital 3 if you remember this, okay? So there are two things. The first thing is that the first part is about adapting the architecture. So it means that we are going to define a new architecture without adapting the ALU slice. So you cannot change this one, and besides of this one, you can do whatever you wish. You can do it in any way. Okay, that's the first part. And the second part of this question is applying the pipelining so that you are going to make it faster. Okay, so let me tell you one thing. Adapting the architecture, you can do it in any way. Normally, you know the slaves from your first year course, you can use any slave. It is going to execute the given extra functions. That's the first thing. And pipelining means that you should define at the first place the pipeline stage. Because if you have the pipeline stage, that is very easy. The only thing what you do, put there the registers. Pipelining means putting registers, nothing more than that. Okay? So that's why it is very important that you define the pipeline stage. At what positions I should have my pipeline registers. Okay, so I see that you have done the first part of this one. This is digital 3, and now we continue with the second part of it. So what are we saying? We are saying that there are 3 extra functions that we should execute with this architecture. And it is not possible, of course, whatever you do, okay, which function you use, whether add, sub, shift left, etc., etc., you cannot execute these 3 functions. Now, what are these 3 functions? If you go down a little bit, I would like to see actually indeed set. The first function is set. I'm going to put it here. Set. And this means, what is the function of it? Accumulator is 1. 50. 1, 1, 1, 1. Indeed. So accumulator is 50. And the other function is, what is it? Not. So this means my accumulator should be accumulator. Yeah, so it is bitwise, don't forget. Don't think that we are going to, because in this case, if it is not bitwise, it is either true or false. You know it from your embedded systems 1 course, okay? That's why this is bitwise. So we are going to just, okay, invert every bit of the accumulator 1 by 1, okay? And last thing is clear, and this one is going to be 0. Accumulator is 0. So let us take, for example, clear. Can I execute it with one of these functions without adapting the architecture? Because this is our first goal. If we can do it without adapting it, then there's no problem. So if I use the add, no, I will never get actually in my accumulator the 0. If I use the sub, I will never get actually this in my 0, because otherwise I should know what my accumulator exactly is, and then apply the same value at the operand. Then it is possible, but I don't know it. So I can not do the shift, use the shift left, not the AND, not the OR, not the XOR. Okay? So therefore, it means that I cannot do it with this architecture. I have started with a clear. So what can I do now? So for example, yeah, let me give you just 2 of them. Okay? And I don't care whether your architecture is going to be minimal or not. Okay? It could be anything. You can put there many components. If it is executing the function, then there's no problem. Okay? So I can do 2 things. This is my accumulator. What I do, I put here, for example, a multiplexer. Another one there, another one there, another one there. So the one input of my multiplexer is this one, isn't it? Where is my, no, sorry. Yeah. Let me change this one then. Yeah. This sum is going to the accumulator, okay? By the next clock pass, it will come there. Yeah. So I did exactly the same. This is accumulator.
The accumulator is an input to...
Yeah, it should be an output where I put, okay. This is some, this is accumulator. Don't change the architecture in this way, but just. So what I did, okay, I put here the multiplexer. Yeah, this is just one of the solutions. I will not walk through all of the solutions, okay? I can also put the accumulators at the input, okay? Don't forget it. I mean the multiplexers. So that I can select the 0, for example, and I can load it. Yet if there are many possibilities, I don't care which one you're going to use. Yeah, so if I put my multiplexers here, and one of the inputs is this, and the other one is just the 0. You see, for example, 0, 0. Yes? So, if I select here, this means that I should have, because it's a multiplexer with 2 inputs, I should have a controller line, isn't it? So let's say cell M or something like this. Yes? So if I select here the 0, by the next clock pass, my sum will be equal to the accumulator, and I am going to do the clear. I can do exactly the same here. Put here actually the multiplexer, select the 0, and choose the load function here. Yeah, choose the load function here. Okay? Because the 0 here then will be loaded in my accumulator. This is another solution. Therefore, I'm just giving you some hints and one solution. Clear? Now, in this way, we can do it. Another one, for example, accumulator is 15. Okay, 15. So I'm not paying attention to the optimizing the circuit. Okay. So the 15, what I can do, add another line to there, isn't it? With 1, for example. So this means this is going to be now 2 bits because I have 3 inputs. So if I select here 1 and load it and again, it is also possible there. Okay. Yeah, so 1 means that my sum will be equal to accumulator. After a while, I'm going to add it here. And last thing here, okay, last thing here, you cannot do it actually with this one. Or maybe, yes, by applying here different kind of techniques. One function and then the other one, etc., etc. But you see that there is a problem. So what I have actually now, I have solved these 2. To solve this one here, okay, what I did, I put here, for example, a multiplexer with this input 1. Look, if you have done it in this way, then I don't have any problem. It's not optimal, okay? Yeah. So I'm selecting here the 1, and I am executing here which function? The XOR, isn't it? In this way, I'm going to get this one there. Now you see that this architecture is not optimal. So this means that I should send another line, cell MT or something like this, okay, to do this. But while I'm having this, then it is possible that I can delete this and put everything there. Yes? Should we do this? This is very easy, of course, okay, to execute the 2 functions. Let us do indeed this one. So I'm just deleting this. Here now, and I'm putting there my multiplexer. My multiplexer with 0, 1, 1, 0, 1, 0, 1, 0. So this one goes to all of them, okay? I'm not going to throw it. So this is cell M, and then 2 bits. Correct? Now, what should I do now? I should adapt the table so that these functions are possible. Let us try to do it. Now, therefore, what I have here, let me do it with this one. My outputs, as you see, because we should design this one here, isn't it? So my outputs are going to be extended with cell M. And suppose that this one, the 1, is going to be 0, 0. Normal OPMD is going to be 1, 0. and 0 is going to be 1, 1. Suppose, I don't know, okay? It's just a coding. Clear? Good. Now, what am I going to do by the first one? What am I going to do there? We did this?
I started it.
Okay. Let me delete it and then, okay. This is not really complete, actually, what we have. This one was the add carry, isn't it?
Yeah.
So in fact, these two are the same as this one there, okay?
Okay.
But anyway, let's make it T at the first place and then continue. So, without doing this, let's do actually the first part. So, I have here this was the add, isn't it?
Yeah.
And this one is add carry, isn't it?
Yes. Yeah.
Okay, good. So what my A slice is doing only adds, correct? Only add, not add carry. That's what we are stating in this one, okay, in the table. So let me delete this 2. Yeah. This 2 here. And let me delete this 2 here. Okay. So let us start actually from the first one, A, okay? We have discussed the B and C. Now we should adapt it, but let's go back to the first one. So in fact, this is the 2. Given a block, given functions, can I make a truth table, in fact? Okay? So this one is add. Now, what is the meaning of add? The meaning of add is the following from your first year course or from your computer architectures or whatever. I don't know what you have got. That's why I do not know it. I know that's not good. That's one thing that I know, okay? By the way, add means that we are going to add 2 numbers together, A and B, and my carry input is going to be 0. Therefore, in fact, normal add means A plus B plus C. This is the normal, okay, addition with this one, the carry, isn't it? That's the normal one. But add means that carry is equal to 0. Yeah? Carry is equal to 0. So if I go back to my architecture, therefore, if my A slice is going to do an add, then this signal here should be a 0. So how can I get there a 0? By making this one the right one.
Yeah.
And it is actually 1, 1. Therefore, my cell C in, yeah, this one there, yeah, it should be 1, 1. Okay, and my action, my A slice should execute the function add. And the code for add is 0, 0, 0. Correct up to now?
Yeah.
So if I add, again, digital 1, okay, I go back to digital 1. If I add 2 numbers, is it possible that I can get a carry? Yes, indeed. Indeed, I can get a carry. So I should put the carry in a memory. Otherwise, I cannot use it for the next operation. Whether I'm going to use it or not, I don't care. Okay, because I do not know what the next operation is going to be. But I should keep it in the memory. So how can I keep, here I'm going to get the carry, how can I keep it actually in memory? By putting it in this D flip-flop, isn't it? That's what we have here. Okay, this is the flip-flop. So it means that this LDCF must be a 1, load. Okay, a 1. Clear? Must be a 1. So in this case, what I do, I execute the add function with carry input 0. And if there is a carry, I put it in my flip-flop. This is the first one. Any question up to now? Now, let us go to the next one, this one. Okay, add carry. So add carry means, in fact, indeed, okay, this one, ADC means A plus B plus carry. Okay, so this means that I should put the carry there, isn't it? So how can I put the carry there? By making this one 0, 1. So this should be 0, 1. And what is the function of this one? It is executing the same function, the add, isn't it? because I had the carry